Today we are going to be talking about the moment of inertia. But first, some pedantry. We are not going to be talking about the moment of inertia. We are going to be talking about the second moment of area. We often call it the moment of inertia, or maybe the moment of inertia of area, because the way we calculate it is similar to how we calculate the moment of inertia in physics. Except even that is not the moment of inertia, that is the second moment of inertia. But because we don't use the actual moment of inertia for anything, we call it the moment of inertia because it's easier. And likewise, we call this the moment of inertia because we are used to it. So, pedantry over. The moment of inertia. Moment of inertia is a tensor quantity. That means that instead of, it's kind of like a vector, but a vector will have an x, a y, and a z component. A tensor can have an xx, xy, xz, yx, yy, etc., etc. Now, because we are talking about area, it is strictly two-dimensional, so the second moment of inertia will have an xx, xy, yx, and yy components. And so we're going to start by talking about the principal components, which is the xx and yy components. We will talk about xy in a later video. So what is moment of inertia? Moment of inertia is a measure of how spread out the area is. The formula for both the xx component and the yy component can be seen here. Looking at the units, y squared has units meter squared, dA has units meter squared, so moment of inertia will have units of meters cubed, or distance cubed, depending on what unit you're using to measure the distance. And it is a measure of how spread out. So the xx component of moment of inertia is basically how far away the area is from the x-axis, and yy component is how far the area is from the y-axis. Moment of inertia is used very often, especially when trying to analyze the failure modes of beams. The xx and yy moments of inertia can tell you how is the beam most likely to fail under a compressive load. And this one right here, called the polar moment of inertia, tells you about how strong the beam is relative to twisting. So for xx and yy, we have for xx a horizontal axis, for yy a vertical axis that go through the cross section of the beam. In the plane of the cross-section of the beam. Whereas for J, the polar moment of inertia, the axis is normal to the cross-section of the beam. For xx and yy, we are then looking for the perpendicular distance, so y squared and x squared. For the polar moment of inertia, we're looking for the distance from that point. But with Pythagorean theorem, r squared is equal to x squared plus y squared, so J is equal to Ixx plus Iyy. Now the moment of inertia does depend on where you take the axis about. It can get larger, it can get smaller, and with a bit of calculus, you can show that the minimum value for moment of inertia is when the axis passes through the centroid of the area. What this means is that different shapes some shapes have very well-defined moments of inertia. I would invite you to look at this Wikipedia page, list of second moments of area, and it does show a bunch of them that you may be interested in. Some are very useful, like a circular cross-section, i.e. a rod. The xx component, Wikipedia just has one x, and it calls J the Iz component. But this is all terminology. The xx and yy are both pi over 4 times r to the 4th power, and if you want, you can integrate this yourself to see, etc. So just one that I would like to point out. A beam situated about its centroid uses the formula 1/12 bh cubed, or b cubed h. So for the x component, b is the distance along the x direction, and h is the distance along the y direction. It is the y direction that gets cubed, because Ixx goes for y squared, and vice versa for the y component. During your homeworks and exams, it is completely acceptable to use a table like this for some of your shapes. For some shapes, you can't use a table like this, but we will see examples of those. Now, what about when the object is not, or when the axis is not going through the centroid of the object? Well, for that, we have what's called the parallel axis theorem. The parallel axis theorem states that if we're going through an axis that is parallel to, but not through the centroid, then we can say that the moment of inertia is equal to the moment of inertia through the centroid, which, remember, was the minimum moment of inertia, plus the area times the separation between those two axes squared. One last thing. Because moment of inertia is an integration like this, and remember, an integration is basically a sum of an infinite number of infinitesimal pieces, we can say that one object's moment of inertia is the sum of two different objects, as long as those two different objects combine to form the one object. Again, this will make more sense when we do a problem.